So it's pz1, but we're going to call it pi. And then you have all the transitions. And plus the some of the logs of all the observation terms. Okay, so the probability itself was the product of that and that and that over all k, right? So basically, I've just expanded out the giant product which was there, and that was our first step in smoothing and all of that. So it's right there. So you can see the E step is really damn trivial. So basically, for the E step, qk of theta means what? It means I replace little z and little y by capital Z and capital Y. And I take the expectation of this, which now becomes random, because I'm calling these random variables now, but with the kth model. And so let's try to do this. Oh, wait. Yeah, the randomness is from the kth model. So let me carefully write this down. So I've got what's the expectation of this with respect to the kth model when I take z to be random? It looks like it's going to involve this for t equals 1.
Would it be h of pi?
What? Now, all right, I don't know what h of pi is. Forget it. The expectation of this with what? No, I don't want anything like that. I've had algorithms here. No, there's no interpretation. No, entropy, I don't know. No, I'm talking about the algorithm. I'm trying to draw out the algorithm. There's no, I want to take, let me write down, so let's see. This will help. This was too abstract, I realized. Let me put it down. So qk of theta, remember, is equal to this, the log. I take the log of the probability mass function of the complete data, zy, given, with model theta. That's where the theta dependency is. And I take the expectation where zy are distributed according to the kth model. And so that's the expectation of this whole big sum. And what I was asking is, what's the first term here? It's going to be just, z1 just takes on a finite number of values. So we've got a name for it right there. Sorry. Yeah. Let's do it like that. Okay. All right, so first of all, I've got the mean of this, the probability of any possible I. z1 can take on values 1, 2, 3, 4 up to n. So pi sub I is just pi of I. Right? And that's the probability that z1 is equal to I, given the data. And then I've got these guys. I just have here. I just have the probability of a pair occurring, and it's, you know, sum over all I and j. And then it's so there. So it's here. I'm looking at time k. So k. All right, so I'm looking at the probability that zk is I, zk plus 1 equals j. That's its probability right here, given the data. And then this last thing as well, similar. And do I have a symbol for that? What is it? Tell me. Somebody else tell me. So I'm given y equals y, and I want to take this probability. How do I deal with that monster? Well, y is given, so it's just what I was saying before. And so we just have to worry about that. And so it's only a zk, so it's my friend here. All right, so there's qk of theta. Stare at this for a minute. What the hell does that mean? Probably. Oh, no, I think. No, oh, I see. Yeah. It's just, you know, you fall. That's why we have to stop soon. This is too much. Oh, wait, no, wait. Wait. No, it's okay. This is a probability. It was okay. No, I think it was okay. So B I Y K. I think it's okay. So just, it's a bit hard because of the notation. So basically, I've got these conditional probabilities. You know, you see, I've got a theta k hidden in there. This is the probability with respect to the kth model. And so here, what I'm doing is I stuck in the random variable zk, assuming it's obtained from the model theta k. All right. Yeah, this is just a variable. This is for any sequence. So first of all, I start off here just saying for any sequence I have this. Yeah. No, it's good.
I thought the YZ was a super. I thought it was,
Oh.
I didn't realize it was a subscript.
Oh, okay, cool. Yeah, no, it's just, yeah, it's hard. The notation sucks. I don't think it can be improved. But what does this all mean, everybody? So, you know, tell me, where did everything? So theta, we said the start was pi or PZ1, and the observation matrix and the transition matrix. So you see that, you know, so dig out where theta is. Theta is there, and it's there, and it's there, right? And this is based on the previous model. And I just realized I used k for time and for iteration. I apologize. That k, you know, should be an L or something. I don't know. Anyway, all right. So now what do you do?
Can you explain the meaning?
What? The meaning. There's no meaning here. Absolutely no meaning. Oh my God, there's no meaning.
Give us like the best interpretation.
There's no interpretation. No. There's EM, which is a strange hack, which has beautiful properties. And then there's trying to apply EM to a hidden Markov model. And so we have the log of the probability of the complete data, and we're just trying to expand it out and understand what the hell we're trying to do. And so it turns out the E step is trivial, as you can see. The interpretation is E step trivial. So to code this is trivial as long as you've got a package to run this. So given the kth model, you have to run the forward-backwards algorithm to compute these guys. So the big computational overhead is right there. You gotta get these guys. But once you store these guys in memory, then wham, you've got these guys here. So E step. So interpretation E step, piece of cake. All right.
Is the gamma is key?
Probably.
First one. Gamma is.
No, 1. The first one's 1, because here we're talking about time 1. So basically plugging in the random, a random variable z1 from model k. So so I stand by that, and I stand by that. We're going from I to j, probability of going from I to j at time L given the data.
So we get these three main terms because one of them comes from the initial condition parameters.
No,
and then one of them comes from the A. One of them
Yeah, no, I didn't want to expand out the product because we did it already for smoothing. Just look at this log. It was from a product.
That's the structure of the equation. Right?
That's because of the fact that the complete data is just a product of a whole bunch of mess. It's I still didn't, maybe I should have written it down before, but I can write down the beginning of it, but not the whole thing. I mean, it's just don't you remember it's equal to the probability, of the prior times the probability of going from, I guess I used lowercase.
You use rho before rho z.
No, forget it. I don't know. There are all sorts of normalizations. Notation. I don't want to talk about notation. The probability of a string is just a big product of terms. All right. No. Hold on a second. In the analysis of the filter, we introduced all sorts of rows and things for unnormalized transition matrices. But the simple thing of this is just a probability of two strings, a string of states and a string of observations. And I'm expanding it out for you right here. There's no rows. It's in fact it might be clearer to just write it out.
Call pi times a times b before that was 1.
No, it wasn't. Actually, I don't want to debate right now. Okay, well we can do that later. You know what I mean? That's not helpful. I mean, what notation I used before, we can sort that out. But that's not. This isn't about that. Yeah. I'm just saying that go back and look at your notes, and you'll know that the whole point of the Markov structure is the probability of a string is I've got the probability of the string of z's times the probability of the string of y's, because they have all this independent structure we put in. So the notation, forget, I don't care about that. This is just a fact. So you go from this, and you just take the log of a product is the sum of the logs, okay? So the fact that it wasn't clear, I could see that, all right? But it should be now. This is a fact. That the probability of a pair of strings is a product of the probabilities because of this wonderful conditional independence. Right? So something to check. But again, the interpretation is again, the E step is simple. What about the max step? What?
You want to maximize its concave, right?
Yeah, well, the thing is that, yeah, that's right. So we want to max, well, so first of all, yeah, things to note. First of all, it's separable. We've got this optimization problem, and we could maximize over pi there. We've got a big funky function of aij, there. They're connected because we're looking at some max over probability measures, and then we maximize the b's separately. So that's an awesome fact. 2, we can apply calculus, as you say. And actually the pi, as I said, forget it. We only have one observation. We're not going to be doing much maximizing. So we'll assume pi is given. Yeah, this is log is concave, and it looks like a piece of cake. But don't forget, it's a constrained optimization problem. So the optimization variables, like the aij's, A is a transition matrix. The fact that A is a transition matrix and B is a observation matrix puts hard constraints, non-negativity and the sum to 1 on the second entry. It appears that would make things hard. Oh, it's so tempting. We shouldn't put this off till next time. I don't know. We should, huh? Coffee time? Yeah. All right, coffee time. But based on everything we learned about relative entropy and convex duality, and in the large deviations part of the course, it turns out we can use that to get a really elegant form for the maximizer. So I guess I'll just wait till next time. So next time, because it is pretty. I mean, so it turns out that this maximization, it looks like you would take a gradient set equal to 0. These constraints make that a little hard. We could put in Lagrange multipliers, but again, you can use our relative entropy ideas and get an absolutely beautiful formula for the maximizer. So you end up with getting, I'm not going to repeat this next lecture, I'm not going to write this ever down again in my life, but you get this simple form for this, a completely trivial form for the maximizer, and you go back and forth and it looks like it's 2 lines of code, except for the 100 lines of code right there. Okay, all right. So yeah, a good time to stop. So I propose that there's no office hours today. I will be available for questions for half an hour if you need me, or so. I don't see why we need office hours right now. But again, I'd be happy to maybe half hour, 45 minutes, and more fun next time. And can you do me a favor? My boss, Professor Harris, asked me to plead with you. You can turn that off.